Welcome back. In this video, we'll talk about numbering and coding systems. Specifically, we need to know how to convert back and forth between binary and decimal and between binary and hex. And we'll also look at ASCII coding. You've probably encountered this material before. The difference is that in this class, we're first going to review the material and we'll be using these conversions for the rest of the course. Let's start with binary numbers and counting. And to keep it simple, we'll restrict ourselves to 4 bits. 0 is just 0, no matter how many bits you have. We add 1, we get 0, 0, 0, 1. If I add 1, 1 and 1 is 0, carrier 1. And then I add 1 more to get 3. Now let's add 1. 1 and 1 is 0, carrier 1. 1 in the carry is 0, carrier 1, and so forth. It's a good idea to work with the binary digits to represent 0 through 15 because we're going to be using these a lot. One easy trick I use to memorize them is that notice that 10 looks like 10, 10, and then I can count up from there. So how many unique numbers can be represented in a certain number of bits? Well, that's 2 to the n. So in this case, we have 2 to the 4, which is 16. We're going to reserve one of those bit patterns for 0, so that means we can represent from 0 to 15. We'll look at 2 different methods to convert decimal numbers to binary. The first one just uses the concept of weight or place value. For example, we see the weights or the place values written on this line. This is just 2 to the 0, 2 to the 1, and so forth. Or in other words, you can just start with 1 and multiply by 2. So let's say I want to convert 39. I can subtract 32 from 39, so I'll put a 1 there. And then once I subtract the 32, I have 7 left. I cannot subtract 16, so I put a 0. Cannot subtract 8, I put a 0. And I can get 7 by adding 4 plus 2 plus 1. So my end result here is that 39 in decimal is 100111 in binary. Let's practice that by converting 43 to binary. First, I'll write my place values. And apologies for my handwriting. So I can subtract 32 from 43. I'll put a 1 there. That leaves us with 11. Just to make it more visual, I'll subtract over here. 43 minus 32 gives us 11. I cannot subtract 16 from 11. I put a 0. I can subtract 8, so I'll put a 1. Cannot subtract 4. I can subtract 2. That'll leave us with a 1 here. So 43 in decimal is 101011 in binary. The first method for converting decimal numbers to binary that we talked about works well for small integers. When the numbers start to get a little bigger, I prefer the method I'm about to show you next. And that's to repeatedly divide the number by 2, keeping track of the remainders. We show that in the box here in kind of a longhand form. I usually prefer to write a table. Alright, so we're going to convert 25 to binary, and I'm going to keep track of the remainders over here. So 25 divided by 2 is 12, remainder 1. 12 divided by 2 is 6, remainder 0. 6 divided by 2 is 3, remainder 0. 3 divided by 2 is 1, remainder 1. 1 divided by 2 is 0, remainder 1. And I can quit when I get 0 in the left column. The trick is to read the remainders bottom up. So that gives us 1, 1, 0, 0, 1. All right, let's practice that on a different number. 36 divided by 2 is 18, remainder 0. 18 divided by 2 is 9, remainder 0. 9 divided by 2 is 4, remainder 1. 4 divided by 2 is 2, remainder 0. 2 divided by 2 is 1, remainder 0. And 1 divided by 2 is 0, remainder 1. Reading our numbers from bottom up, we get 1, 0, 0, 1, 0, 0. And if we want to check, we could use place value. This is 1, 2, 4. This is 8, 16, 32. 32 and 4 is 36. And we can also use place value to convert binary to decimal. Let's say we have the binary number 110101. I know that this place value here is 1. That would be 2. This is 4. That would be 8. That would be 16 and 32. So that would be 32 plus 20 would give us 52 plus 1 is 53. Converting between hex and binary is a simple direct mapping. So you can take any 4 bits, let's say 1001, and map that to the hex digit 9. So in hex, of course, we start with 0 and 9, and then once we run out of digits, we use A through F, either uppercase or lowercase. So let's just make up an arbitrary string here. We'll start with the least significant bit on the right, and I'll draw kind of a squiggly line to separate 4 bits. This is 6, and this is 5. So 1010110 in binary would be 56 in hex. And of course you can go the other way as well. The discussion so far assumed that we're using all of the bits to represent the number. That's unsigned integers. We also need to represent signed integers. We'll do that with 2's complement. The idea of 2's complement is that you're going to take half of your bit patterns and reserve those for positive numbers and reserve the other half for negative numbers. Then we can look at the most significant bit, the leftmost bit. If it's a 1, that means it's a negative number. The range of our numbers in a 4-bit world will be from -8 to +7. I'm going to show you 2 methods to convert a number to its 2's complement representation. The first method involves 3 simple steps. First, we write the number as if it were positive. So for example, if we want to represent -5, we write +5. And I'm going to write it in 8 bits here. Alright, so that's step 1. Step 2 says to invert each bit. That's sometimes called the 1's complement. And step 3 is to add 1. So our number is 1111, 1011. We would write that in MIPS in hex as 0x, FB. Other languages, as you see down here, may use a different notation. Now I'm going to show you a shortcut method. So it starts off the same. We write the number in its positive form, so using 5 again, and I'll use 8 bits. Here's 5 in its positive form. And then the idea is going right to left. We're going to copy through the first 1, which we hit right here. And then from then on, we'll invert all of the bits. Let's try that with a different number. Let's try it with 4. And again, I'll use 8 bits. Again, going right to left, copy through the first 1. So whatever 0s and 1s you encounter, through the first 1. And then from then on, we invert. This method is reversible, so follow the same rules. Go right to left, copy through the first 1, and then invert all the bits. When a signed number is moved to a larger memory unit, the sign is extended to the left. In a signed number 2's complement, the most significant bit is the leftmost bit. And this would get extended to the left to represent either a positive or a negative number. Let's practice adding a couple of binary numbers. Step 1 would be to convert the number to binary. Positive 11 would be 0, 0, 0, 0, 1, 0, 1, 1. I'm going to use my shortcut to find the negative. So I'm going to copy right to left through the first one and then invert all the bits. Alright, so negative 11 is 1, 1, 1, 1, 0, 1, 0, 1, and 8, positive 8, in 8 bits is 0, 0, 0, 0, 1, 0, 0, 0. So if we add these together, we get 1, 0, 1, 1, and all ones. So the question is, what number is that? Let me use my shortcut to convert this 2's complement to its positive form. I'll copy right to left through the first one and then invert all the bits, and I see that it's 3. So that is the correct answer. We'll look at many more examples of binary addition in class. So we've seen how unsigned and signed integers are represented. How are characters represented? The assembly language we'll use, MIPS, uses ASCII representation. ASCII has been around for about 50 years. It stands for American Standard Code for Information Interchange, and it can represent everything that you see on a standard keyboard. It uses 7 bits per character, really 1 byte, and this was adequate until the age of the Internet. Then we needed to be able to represent all of the languages, and that led to the development of Unicode. Here's the ASCII table showing you which characters can be represented in this encoding scheme. Notice some nice things about this. One is that the digits 0 through 9 can be represented as 30 through 39 in hex. So what that would mean is that if you, let's say you read in a digit as a character 30, let's say it was 0, and you wanted to convert it to an integer, all you'd have to do is subtract the 30. Other nice things about this system are that if we look at the lowercase and uppercase here, so let's just look at uppercase A and then lowercase a, you can see that you could simply add or subtract 20 in hex to convert from upper to lowercase. When we use character data in MIPS, we'll be using ASCII data. So going forward, you do need to know how to convert between decimal and binary, and between hex and binary, and how to represent either signed or unsigned integers, and also how to add binary numbers. We'll practice all of this in class. See you soon.